ago. Um, and I think the first time I met him was at Berkeley. I was visiting Berkeley and was talking to Paul Richards, who is another giant in the field. And he introduced me to Shaul, and he said, you know, there are two kinds of experimentalists. They're the kinds who plan things out in detail and never get anything done. And then there are people who plan things out in detail and jump into things and get results. And so Shaul is in the latter category. So today he's not going to be talking about cosmology or CMB. He's going to be talking about something that's important to all of us, which is education, particularly undergraduate education. I think it's fair to say he takes the same approach as to experimental physics. He's dived into a project here that I think he recognized was important for the field. And so we're lucky enough to hear, I think, the first colloquium that you've given on this particular topic. So
yes.
I'll let Shaul get going.
Thank you, Peter. I never realized Paul said that. Yes. Pleasure to be here. So the topic for today is integrating computation into the undergraduate physics major. Using computation to engage in problem solving is a central practice of physics. Computation is used in all subfields of physics and is often considered a third mode of inquiry alongside experiments and theory. Computation has played a key role in all recent discoveries from the late 20th century to the present. It's essential for the introduction of new fields like quantum computing, multi-message astrophysics. AI and machine learning are gaining grounds rapidly in physics as well as in other fields. Computation is a required skill for all of our majors for the future careers, whether they go to industry or grad school. And the list of competencies that they require in those careers is continuously growing. I think it's fair to say that it is almost inconceivable to do physics today without computation. Yet, computation is largely not integrated into the undergraduate physics curriculum. By the word computation, I include a very broad and intentionally not so precise array of skills and thinking modalities, including modeling, simulating, predicting, analyzing, and displaying the behavior of physical systems. The overwhelming practice in undergraduate programs is to rely on pen and paper calculations. Even when computation is integrated or even when computation is used, it is used haphazardly by one instructor or the other in an elective class, or maybe it's relegated to a computer science course by the CS department. So a useful comparison point is how we treat math skills compared to computation skills. And I'm not saying that math is exactly identical to computation, but at least as far as problem solving is concerned for physics purposes, math is required. Computation are largely not required in our undergraduate programs. Math is covered in 4 semesters in most physics programs in the country. In computation, there's no requirements, and if there is any, it's maybe between 0 and 1, 0 not being required at all, or maybe one course that programs require. And if one looks at the structuring and scaffolding of the program, then math is very well structured and scaffolded. You start with differentials, integrals, linear algebra, differential equations, vector calculus, and then, of course, we have the reinforcement in physics classes. Parenthetically, I think many physics instructors would say that the math students get in the math classes is useless. Nevertheless, it's there, and we reinforce upon it. But whatever is done in physics is not scaffolded, it's not structured. There's a broad consensus that we should do better Among US faculty, there's been a number of surveys. So from Fuller 2006 and Chanaki and Winch, they have done a survey, and this is a quote. Computed numerical approaches to learning physics principles ought to share stage with analytic approaches. That was a question. And more than 80% of faculty who were interviewed are either agree or strongly disagree, or strongly agree, sorry. In that same survey, and in a later survey by Caballero and Merner, most faculty also agree that it is not integrated, that computation is not integrated into the curriculum. The AAPT has instituted a policy in 2011 facing this challenge, saying that every physics and astronomy department should provide its majors with appropriate instruction in computational physics. The American Physical Society and American Association of Physics Teachers in 2016 released a report titled Physics 21, Preparing Physics Students for the 21st Century Careers. And in that report, they state that there is broad consensus among stakeholders about what skills graduates should have. And there is also consensus about the skills that they are lacking. And I quote, studies of physics graduates conclude that their technical skills should be expanded to address a wider and deeper knowledge of computational analysis tools. And the report recommended specifically new learning goals for the undergraduate career, for the programs, and again, quote, demonstrate software competency, demonstrate coding competency, demonstrate data analytic competency. The American Association of Physics Teachers released a report, Recommendations for Computational Physics in Undergraduate Physics Curriculum. And they say all physics majors should develop and practice these skills over the entire range, over the entire span of their degree program. And finally, I believe many of you are familiar with the APS and AAPT EP3 guides, Effective Practices for Physics Programs. And specifically, they talk about computational skills. Adding these skills to the curriculum addresses a common weakness that many physics graduates report in their undergraduate programs. There's been no lack of efforts to integrate computation into the curriculum. Starting from 1988, McDonald, Reddish, and Wilson published the Muppet Manifesto, and they advocated, particularly for introductory physics, to use emerging computational tools. Then in 2001, Gould and Tobochnik build some more about this, and they advocate doing simulations. In the early 2000s, the University of Oslo has completely revised its curriculum, the physics department. And since the 2000s, they are completely integrated into computation, a quite unique experience. In 2006, a number of people built up a pickup program, physics, I don't remember please, integrating computation into the undergraduate physics programs. And so this is building a community of practice of instructors who are using computation. In 2008, the University of Oregon has implemented in its upper level courses, and Lawrence University published a program-wide. And more recently, Indiana University, Indianapolis has integrated computation, and Michigan State is undergoing a process. But overall, this is a small number of programs over the country. And what I want to tell you about today is the approach we have been taking at the University of Minnesota. I will talk about the approach, the process, the challenges, and I hope time permits that I have a couple of slides in the end to talk about a new project we have embarked upon to integrate computation in a larger number of institutions. I want to give thanks to my colleagues at the University of Minnesota, primarily Ken Heller, who has a long history in physics education research. I'm not a physics education research by my own. As I said to some other people that I met today, I'm just a physicist dude who stumbled upon a gaping hole. Ken has been an inspiration with his knowledge, and these are Tom, Joe, and Alexis are my co-investigators for the NSF grant that supports us. So to frame the problem, I want to make a clear, I want to phrase a clear goal and our metric for success. The goal is to normalize computation as a problem-solving method throughout the physics curriculum. And so several principles derive from this goal. The first principle is computation is to be integrated into the required courses. It should not be a single computer science course, or should be relegated to a single computer science course. It should not be a single, even computational physics course, let's say done once. And it should not be constrained to an elective course. For example, that computational physics, like it was in Minnesota, we have a computational physics course, but it is an elective, and 10% of the students take the course. It should be part of the required courses. If you are to integrate computation, then it needs to be integrated into all instruction modalities, not just as a homework in one time in the semester in a given course. You do it in class, in homework, in assessments, just like you do everything else. If we do that, we have to do it in a structured way, in a scaffolded and reinforced way. And bearing in mind that we're not here to teach computation, we're here to teach physics. So whatever you structure, you have to keep in mind that computation serves the physics. The physics is the driver, not the computation. And this is by no means intended to displace pen and paper calculations. Pen and paper calculations are enormously important. It is in addition to, not instead of. There are requirements that derive from these principles. First and foremost, choices must be made. Computation is so broad and so large, if you choose to integrate it, you have to integrate a small, focused number of elements. You don't want to displace pen and paper calculations. You want to keep the emphasis on physics. So you have to know what you want to do. And whatever you do, you might as well do it in a sustainable way. So here is a sketch of my view of change, educational change, or in fact, most changes. Here's a magnitude of change as a function of time. Most change processes ramp up, go down, and go to zero after some time. That's not worth the effort that you put here under the integral. The hope is you go up, and a little bit more than epsilon stays. I'm under no illusion that we go up and we will stay there. But you might as well do it in such a way that something will remain. So a few words about the program at Minnesota. We have 14 required courses, shown here in blue and green. Of course, the red one are the math requirements, but those are part of the required, but they're not physics. We have 5 tracks. We have a track for computational physics, so people who want to do that can do that. We have a handful of students, less than a handful, doing it every year, and they have more students in computation and CS. But most students choose what we call the professional physics, and all of these courses are the requirements for the professional physics. There's no requirement to take a programming class. About 60–70% do take a CS programming class, but not all. And those 70%, some of them take Java, some of them take Python, some of them take C, so it's not uniform. There is, as I mentioned, an elective senior level class, computational physics. Only about, as I said, 10–15% of the students take that class. Some courses are offered twice a year, some are only once. We have to think about the astro students, and not only the astro, we have to think about the astrophysics majors who take many of the physics classes, and they cannot take these classes in this order. This is sort of the nominal order, but many students don't take the classes in that order. Physics 1 and Physics 2, we do not have courses for physics majors. Our physics majors take the classes with our other service for engineers. So those are 1,500. This is a 1,500 student class taught with 6 or 7 sections. So right off the bat, I'll tell you, we are not doing anything in computation in those courses in our introductory level because it's way too complicated to serve our students together with the engineers. I know that in Wisconsin, you have your own Physics 1 and 2 class for majors. We don't have that in Minnesota. Let's see, what else I want to say. I think that's it. I want to pay specific attention, or I would like you to pay specific attention to these 3 courses: Modern Physics Lab, 4th semester. Analytical Mechanics, it's the junior, senior level mechanics. And E&M, the 7th semester, first in a series of 2 Griffiths-based E&M. We're going to talk more about those courses momentarily. Our department is not that different than yours. You'll probably see many things similar. Total, we have about 60 faculty, astronomy and physics together, all one department, not like 2 here. We have nominally a 3-year instruction cycle. We have a questionnaire. We fill out a questionnaire every year. Assignments are done every year, but we try to respect instructors' preferences for 3 years. That's not rigid. Sometimes if there are special circumstances, instructor will instruct less and sometimes longer. But that is the cycle, and it gives an idea that instructors are not assigned to classes for 15, 20 years, in which you get to embed a specific thing, and that's it. Whatever you do, 3 years later, someone else will throw it away and will do their own thing, most likely. We do have core material published on a wiki site available for all faculty. So you have probably seen with the program that the program follows the standard physics canon that you have: mechanics, thermal, quantum mechanics, E&M, and so on and so forth. And we write the core curriculum for every one of those courses. Nobody actually monitors and nobody enforces. So this is there for mainly new instructors. Here's what we expect you to cover. Here's what's covered in the earlier classes. Here's what will be covered and will be assumed that you'll cover in this class. TAs is an involving story. The TAs, the grad students, have unionized university-wide in Minnesota. So that has created a cascade of changes. And so this is an evolving story where we have now moved to less graduate students supporting classes. I'll talk more about TAs a little bit later. In terms of management, we have a head, director of undergrad education, and an undergraduate education committee. This is sort of more the executive arm, and this is more the advisory arm. These days, we have another committee, which is the Computation Integration Committee. I'll talk about this later, who is who's working in close contact with the other committee. And as far as communication within the department, most communication with faculty is done through faculty meetings. And so most of them are, I don't know exactly how this is done here. We have few of them, not every week, few of them per semester, maybe 4, 5, 6 per semester. And these are mostly a report style, not so much a discussion style. So as far as the implementation for the integration, so far this was just a review to give you a background of how the department looks like. So to implement, we decided whatever changes we make, the changes will be staged and implemented slowly. I don't know if they will be supported actively, but definitely we don't want to input anything that will incite strong opposition. So if we sense that something doesn't seem to work, and I have examples, then we try to change direction, just to make sure that everyone is on board with whatever we're doing. Changes should do no harm, and I'll show you how we test that. Some educational changes maybe are very valuable for some aspects of the education, but they can actually degrade the overall student experience. So we try to make sure that that doesn't happen. We adopted a single computation platform, MATLAB. I want to make sure that you understand that none of this discussion here that we have today is about the platform. 99% of what I'm going to talk about is platform independent. We did choose to adopt a single platform so we can support students, TAs, and instructors with one thing, and we don't have to develop expertise in 2 or 3 or 4 different platforms. But everything else from now on that I'm going to describe is going to be platform independent. And if anyone wants to know why we're not doing Python, why we chose Mathematica, I'm happy to talk about it later. Things to keep in mind is, as I said earlier, we have double majors, we have transfer students, we have others that are not taking courses in the order prescribed, and we have to keep in mind that graduate TAs have not graduated or have come from programs that do not have computation integrated. Of course, I think many of you know that the most prevalent paradigm in instruction is do upon your students what have been done to you. It's not a good paradigm. Nevertheless, this is what's being done. And so that's what the graduate students know. And when you ask them to teach with computation, they're, what am I supposed to do now? So that has been a challenge, and I'll talk about this just briefly later. So here's what we do. We selected a specific set of computation competencies. For those competencies, we selected specific topics. We mapped those topics to courses, and then we are developing the instructional material. So here's how this looks like. We chose 4 computation competencies: coding, mathematical modeling, presentation and visualization, and validation and verification. I'll make those concrete in a moment. But what's important is what we consciously excluded. And you have to decide if you go on this in a structured way. These are things that you have to decide ahead of time and very consciously and clearly. We're not doing parallel computation. We're not doing simulations. We're not doing AI and machine learning. Is this good or bad? Different departments can make their own choices. The important thing is that choices must be made. For coding, for example, we choose a very small set of coding topics that we want to cover in an intentional way. I think all of you will recognize there's much more to coding than these 7 boxes. You know, code writing, array operations, read from and to a file, functions, loops, if-else, documentation. I mean, this is 3 weeks in a CS class, right, in a computer science class. But that's what we want to make sure students graduate in the end of 4 years. We need to make that sure in the first year for them to do anything. But we're not striving for anything more than that. This is what mathematical modeling topics we include. There's a bunch of topics in statistics. You know, the obvious, fitting, chi-squared, probability to exceed, probability distribution function, cumulative distribution function. This is covariance and correlation is a little bit graded because this is optional, not required. Then we have differential equations, matrices, eigenvalues, eigenvectors, numeric integration, Fourier series, and the concept of normalized units. Again, the world of computational, of mathematical modeling is much vaster and broader. Presentation and visualization. Obviously, we have picked some number of topics. You would be surprised how many of the grad students don't know, let alone undergrads, let alone some of my own colleagues, don't know how to make figures properly with readable font, axis labels, legends. The very, very basic. Multiple data sets, log, surface plots, stream plots, and so on and so forth. And validation and verification. Everything you do has to be validated and verified. So here's the mapping. So now we're here in the mapping. And so I'm not going to do this for all of these. I just want to illustrate how the mathematical modeling topics map into several courses. So the Modern Physics Lab, MPL, most of the statistics fall into the Modern Physics Lab. It could also fit thermal physics or statistical physics, some of it. I'm not showing all mapping into all the required courses, but we have done the mapping. Mechanics fits very well with differential equations and moments of inertia, for example, normal modes. Numeric integration is really fantastic with E&M. Modern Physics Lab, Fourier series, both mechanics and E&M, where you do driven mechanical systems and boundary value problems, which I'm doing right now with my students in E&M. And normalized units, of course, fits almost everywhere. And so now, here is how Modern Physics Lab looks like in terms of its computation integration core curriculum. This is the first course that we are doing computation integration into. It's the 4th semester. And I'm sure there's going to be questions, why are we waiting for the 4th semester? It's a good question. But at the moment, that's what we do. So we start with a MATLAB on-ramp. It's an hour and a half, 2-hour on-ramp course provided by MATLAB. Really, really good course. Parenthetically, MATLAB really has excellent help and documentation, close parenthesis. And then during the semester, these are the topics: encoding, computational mathematical modeling, visualization, and verification that we are planning to cover in this class. And it's done slowly, sequentially through the semester. In mechanics, which is the second course, 5th semester, we are building upon reinforcing the earlier topics, and these are the new topics that are intended for that analytical mechanics 5th semester. And I'm not showing the electromagnetism, but you understand how it's built and what is the idea. This all sounds very linear. Nothing in instruction is linear. It all has to go with feedback, and you make errors, and you build a course, and you realize that what you intended for the students to understand from a particular exercise, they understand something completely different, and they don't actually have several of the components you thought they would have. And so you have to change and iterate and improve. And so that's part of the structure. And then there's developing the instructional material and actually implementing that in the courses. So that has its own structure to it. And so here's what we do. So this is the academic year in which this is started at higher intensity. Earlier in 2016 or so, we mandated MATLAB for our courses, and that's it. And this was adopted for Modern Physics Lab. But starting in academic year 2022-23, we started in earnest this integration. And so let's look at Modern Physics Lab. These are the semesters. This is mechanics, E&M, and there's going to be more courses here. We started with one semester of observation. This is sort of, here's how the course is running. Here is where we could integrate and how we could integrate those specific topics that we plan to. This is how we could do it. Then we have a team teaching semester, 2 instructors, 1 frontal, teaching to the students. This particular class has 1 hour a week meeting and 3-hour lab. And so there's a primary instructor and a secondary instructor working in the background together, not in any secret, but there's only one instructor seeing and meeting the students. And the other instructor is dealing with developing the MATLAB, assessing whether it's work, talking with the primary instructor, doing collaboratively with the TAs. We thought for the one single instructor to handle the entire class and the TA meetings and the homework, it would be too much, and it is too much. There's a semester debrief, improvements, another team teaching cycle, another debrief, and then we go into a mentoring, if mentoring particularly meant for new instructors, to try to make that extra sustainability, to ensure sustainability in whatever has been integrated into the class. And so that kind of cycle repeats for the mechanics, observation, team teach, debrief, and so on. We are now here in the fall of 2025, and this is the first semester that we have a new, completely new instructor teaching that course, and we're into the first mentoring session. And mentoring meaning meeting with instructor periodically. Here's the material, here's what we do, here's why we do that, here's what has worked, here's what didn't work. And all you hope is that the instructor will appreciate, not the effort, but appreciate the goals, and will build upon them and will adopt them. Most instructors are happy where when you give them some material, they don't have to invent everything on their own. And this is the first term we're doing team teaching in E&M. I'm actually the primary instructor for E&M, and we have another instructor who is doing the team teaching with me. And with the committee, we are discussing what will be the next course that we will do in the next academic year. Here are some of the outcomes. So this is, I'm showing homework from Modern Physics Lab, the same student. Homework 3, here's a plot. And this is a week later, or I should say 2 weeks, because they are doing 2 weeks here. 2 weeks later is the same student making plots. So this is instruction happening. And so nobody should be surprised with this. Nobody should be surprised, and nobody should be judgmental. Students need to be instructed. That's our role. Here's another example. A different student, but again the same student. A piece of MATLAB code in homework 3, and then we keep saying code needs to be documented. And if you don't document your code, points will be deducted. And maybe the students in homework 4 didn't quite get that, but by homework 7, okay, I get it. So the code is documented. I want to give several examples of not student, well, it will include student work, but a couple of examples of actual example of where we do computation, sort of boots on the ground, as an example. So this is from a mechanics class. The classic pendulum. And all of us recognize this equation, phi dot dot plus g over L sine phi equals 0. Maybe not all of us recognize that this problem cannot be solved analytically, because most of what we do is we say we're going to take sine phi, phi to be small angle, and this is the classic harmonic oscillator. This is obviously great, and we do this so many times in physics, but does everyone really realize that this is not solvable analytically? That it can only be solved numerically? And here is a great opportunity to say this can only be solved numerically. And now, in your 5th semester mechanics, you can actually solve it numerically. And you know, we told you guys that the amplitude is independent of, that the period is independent of the amplitude for small angles, small, let's say being smaller than 20. Well, it is. If you wait enough period, you'll see them diverge from one another. So when you start with 10 degrees, the exact and the harmonic, they look identical. But after 4 or 5 period, if you plot the difference is 5 degrees, and it's, of course, it's increasing. And of course, if you start with a large angle, they diverge immediately. But there's another nice learning lessons here, that you can have non-sinusoid periodic, you know, these the blue, they look exactly like sinusoid, but they're not sinusoid. They're nice periodic numerical solution for with the sine phi. So this is it's just an opportunity to illuminate more of the physics. Here's another opportunity to illuminate more of the physics, again for mechanics. So when you do Coriolis force and deflections, I remember myself, you know, I was amazed by all of this. And here's a coupled set of differential equations. And then the instructor will very quickly teach us, well, you do these and these and these and these approximations, which seemed, when you are an undergrad, they seemed, how would I know to do these approximations in the first place? I mean, it's fine, it's great to know all of this, but as an undergrad, it seems all like black box. Learning those skills is very important. I'm not saying they're not. But here's another opportunity. So here's an example. You shoot a projectile east or north on the equator, or you do east and north in some co-latitude. And lo and behold, you can now solve all of these coupled differential equations. Exactly. You should, and we should show the approximation. And we should show that the approximation in certain limits agree with the numerics, of course. But you can also do this exactly. And finally, my last example is this classic example that I just taught the other week. My students, where you have a linear charge density, and you can calculate the field right here in the middle, and obviously within 3 lines you get the electric field pointing, the vector points straight down. But does everyone really realize that if you move an epsilon left or right, you cannot solve the integral analytically? There's no solution. You have to solve it numerically. So you may wonder, why even ask the students to do that? Well, first of all, there's an educational lesson by, yeah, you can pose this question. What would you do if it was not in the center? Not only that, you can solve the question. This particular integral that's shown here, it repeats itself 3 or 4 or 5 times, the same form, throughout Griffith's 7 chapters that we do in ENM1. And if you're into physics intuition, you could say, I move a little bit to the left. Is the vector here pointing leftward because there's more charge on the right side? Or is the vector pointing rightward because this charge is closer? I'll give you 2 seconds to think about it. The answer is that the 1 over r squared dominates, and the vector points rightward. I mean, if you start here, it's obvious that the vector points here, then it decreases and it goes here. There's no transition. But anyway, you can ask the students the question, and you can improve the physics intuition. All of the educational elements that I talked about will only be sustainable for the long term if they're embedded in another sustainability structure. And that sustainability structure includes faculty buy-in, instructor mentoring, TA training, material accessibility, ease of use, and department management support. So what does that mean? As far as faculty buy-in, how do you generate that? Well, the first and foremost thing, you have to keep talking about what you do in your faculty meetings and in any other faculty meeting or any other faculty gathering that exists. People have to know. People should develop opinions. It's okay for people to like or not like. But if people don't know what you're doing, there's no chance that anyone will come on board. It's very important that anything you do would be perceived as a departmental project, not as a single person enthusiast. Granted, and admittedly, anything new starts with individual initiative. But if it doesn't transcend the individual initiative, it will die over time. So it cannot be a single instructor initiative or just a single course. It cannot remain a single individual that drives this thing. There has to be a committee or an entire department. For example, now we have a standing computation integration departmental committee that is appointed by the head, just like the undergraduate education committee or the graduate education committee. There's a committee that thinks and decides what should the department do next, and that committee discusses this with the undergraduate education committee, and there's a consensus. And you have to solicit faculty input, which we do. For example, we would have a faculty meeting, and then we say anyone who wants to stay can stay for another half an hour, and we're going to talk about these particular topics that involve integration, the integration of computation. We do faculty workshops for faculty who are interested, and of course we do the mentoring and face-to-face discussions. We have built a local computation problem repository that is accessible to all instructors. There are a lot of material available on the web. One of your colleagues here has made available, Duncan has made available MATLAB scripts, fantastic material on the Pickup website, and there's material available on other websites. We thought that if we made this accessible locally for faculty, here is a course packet that we do in mechanics or modern physics lab, this will make it more accessible. And of course, we want to maintain it and to update it regularly. Everything is available here. So the problem PDF, the problem tag, the solution PDF, the solution tag, the solution MLX, this is the MATLAB, TA guide, everything is available to the instructors. And it's very important to have departmental support in terms of the team teaching, of course, that's the department allocates resources, instructor assignment every year, committee assignments, repository management, and overall tone and attitude. This is what we do. It cannot be a single individual saying to the department, this is what we do. TA training and preparation is a key issue. We have not yet We are just starting to grapple with it more properly. So far, we have been doing is on-course preparation, meaning a TA would be assigned. We would talk to the TA as part of the course preparation. This semester, meaning starting the spring semester, starting this winter, we will do actual TA preparation. For all of the TAs, now we have 3 courses with computation integrated material, so we will do a broader training to those TAs who are supporting these courses. Okay. Moving further, how do we assess our performance? So when you ask about assessment, you have to ask, what do you want to assess? So many things can be assessed. And I'm not going to go through all of it. Are students gaining the competencies we plan for them to gain? Do students gain deeper understanding of physics? Do students value the new modality? Has the institution changed? There's so many things you can assess. So I'll tell you what we assess. The one most important thing that we set to do, we're not assessing yet because there's no instrument. We are not assessing whether students have gained the competencies. We are, of course, assessing homework, exams. That's what we do like every course. But are we assessing from beginning to end? No, because there's no instrument to do that yet. That's the topic of another discussion, another mention that I'll do later. We're administrating what's called the CELAS survey, Colorado Attitudes About Physics Survey. It probes beliefs that students have about learning physics. Learning physics changes by ideas about the world, how the world works. And students get to grade this or agree, strongly agree, Likert scale, a neutral, disagree, strongly disagree. And we assess students' beliefs that they can succeed in their physics classes. That's sources of what's called self-efficacy in science courses. For example, I am capable of receiving good grades on my assignments in this class. So do students think that they're capable? What is their attitude? Both of those are the do no harm category. So this is the CELAS, Modern Physics Lab, Analytical Mechanics. This is the SOSEC, Modern Physics Lab. And what you really want is you want to see no change. You hope to see no change, or if anything, improvement. So we're doing reasonably well. There's no obvious degradation after the computation integration begins. Here, maybe within some error bars, there's some change. We don't know. It's the only one we have, so we still have to see. But maybe no harm yet. Here is a survey that I did in fall 2024. At the end of the course, Analytical Mechanics, the use of computation in this course is unnecessary nuisance with little added benefit, or is an overall positive that has benefits. And so 84% of the students say it's an overall positive that has benefits. So that's nice to hear that the students don't see that as a nuisance. Here's my own assessment. I think we've made a lot of progress, but I think challenges remain with TA training. There's still a lot of work that we have to do in terms of year-by-year instructor assignments and new instructor mentoring. In the last 2 minutes that I have, 3 minutes, I want to talk about the new project I said earlier, expanding the computation integration to more physics departments. This is my co-principal investigator, Maria Lopez del Puerto from St. Thomas University. We've put together a collaboration of 9 institutions of various types. Some of them, like the University of Minnesota, with 60 faculty, Penn State, 50 faculty, 48, Ohio State, 66. But we also have Concordia College with 3 faculty, Bridgewater State with 7 faculty, a broad range of institution types, R1 institutions like both of our institutions, but also colleges. The project goals, let me start with the deliverables, and then I'll map them to the goals. We want to come up with a consensus list of computation competencies and learning goals that everyone across the 9 institutions can adapt. This is a good core for physics majors to have among all of those institutions. A list of computation learning goals, an assessment instrument. How do I test that I have given students the competencies over the program? And we would like to come up with 2 or 3, or we would like to come up with certain core elements that would sustain change in a large range of departments, or sustain the computation integration across many departments, because Concordia College or Bridgewater cannot do computation with team teaching like we're doing. They just don't have the number of instructors. So they have to have some different models. The goals: adapt computation integration change process to a broad array of physics departments. And then we use some what we call propagation model to facilitate the spreading into other departments. So here's my summary. Computation integration is a long overdue process. It requires an institutional change process. Whether we are going to be successful in Minnesota, I don't know. We will know in 20, 25 years. Thank you.
Thank you, Shaul. That was inspiring. Questions?
So in my previous life, I interacted a lot with engineers, and my impression was that they did really well about integrating computation into their curriculum. So I was wondering if you interacted at all in designing this with how they do it there.
So we did not interact with the engineers. The engineers are way ahead of us because the engineers, they need to train people who are actually working, go out to the industry, most of them, and they have the ABET certification. And so, for example, MATLAB, if they don't have MATLAB, they cannot get jobs, right? I have communicated with chemistry, more sciencey departments, chemistry, earth science, math, and all of them said, what you're doing is great. It's long overdue for us as well. We have done nothing, and we would like to learn from you what works and what doesn't. Maybe we haven't done enough due diligence with the engineers that we should have done, but it's not too late.
For your proposal with these 9 other institutions, is your plan to produce your list of deliverables, give it to those institutions and see what they do with them, how they're able to actually take action with those, or are they actually collaborating with you to produce that list of deliverables?
We don't give them anything. It's all collaborative, all 9 institutions. We have a process of about a year and a half to come up with a list of competencies and learning topics. All agree with them. They have to agree with their own faculty. So it's not just, so for example, Penn State or Ohio State, they have 50 faculty. So we have 2 representatives from each department. We will think, they will talk to their faculty. Everyone has to come on board. Then we will try to run it for a year or 2. We will develop the assessment model, and then we'll run it and see if it works. But we don't give them anything. Nothing will work if I give someone something.
So with programming, AI is kind of getting better at it. So this is a program seems to be being developed in a time of great flux in the field of how we should might program or teach people to program. So how are you grappling with some of that?
Yeah, great question. This is almost the first question people ask. And I'm not sure that I'm going to have a very satisfactory answer, but let me. Part of the answer is the word you use, programming. We're not trying to teach programming. We're trying to teach computation skills. Now, so that's part of the answer, but that doesn't really address your question. What really addresses your question is almost everything that you can think about in terms of computational integration, the challenges that are faced in terms of AI and LLMs, those are identical to everything we do in physics or in other fields as in computation. So whatever the solutions are there, they're going to port over. And I'll give you an example. Any of the problem in E&M that I'm assigning to my students, and I've checked that myself, I type it into ChatGPT, and I wait a minute, and ChatGPT spits the answer out. Any of these problems. So, of course, that's the problem that's being addressed. You know, how does instruction look like in the world of AI and in LLMs? What I would say, and I wanted to have a, what I would say is that the programming element, the coding element, is definitely becoming just like using a calculator. You can have ChatGPT or any other Claude or Copilot produce the code for you. Is the code doing what it's supposed to do? Is the code validated and verified? That you still have to do. You can't rely, and you shouldn't rely. And so, in terms of actual implementation, I am encouraging my students. You don't know how to do something in MATLAB? Check, check ChatGPT. Check MATLAB AI. But in a quiz on an example or an exam that we just had last week, I gave the students a piece of code in class. I gave them a piece of code. I said, you need to calculate this and that. Here's the code someone wrote for you. Is this code going to work? Right then and there in the exam. Of course, it's designed in such a way that it's not going to work. But that's not the question. The question is, why would it not work? What would you change? The key element being, yes, you can use ChatGPT, you could use Copilot, but you have to understand and you have to develop independence.
I suppose I want to be the one that asks why MATLAB instead of Python. No one's asked it yet. But then I also was wondering, is that how you integrate coding into the assessments? Because I suppose in this world of AI, you can't you can't do a computer test, right?
Right. Yeah. So let me start with the second one. That is the one element I didn't talk about AI, which you're asking about. There's an element in AI which is an element of discipline. So some instructors say, you can't use AI. Don't use it, and I'm going to do everything I can to prevent you from doing this. There's another, some instructors force students to use AI. So I think when we think about AI, I think we need to move away from the discipline side into what are you trying to achieve in your instruction. But the discipline element comes, as you're alluding to, for example, last year or the year before last, our assessment was a take-home. You can do even programming in a regular 50-minute class, but as soon as you open computers, you're facing this question of discipline. How do you make sure the students don't go to some other platforms? And so yes, now this is a new, I don't know to use the word innovation, but in order to avoid the discipline issues involved in using AI where you don't want the students to use AI, we do this. But just to be completely fair, last year when I had an exam, I gave the student a take-home, 2-hour take-home, and I was very explicit. You want to use codes that you developed? Use codes that you developed. Please don't use AI. Please don't use ChatGPT. But it's very difficult to monitor. So to be fair to those students, so for me it's a question of fairness. Some students are going to heed my request and not use ChatGPT, but others won't. And so now we're transitioning maybe to this new model where we can do everything in class and computers are closed. I don't know whether I'm doing the right thing. All of us are finding our way, right?
You've been very clear that your approach is to emphasize the physics and the computation is to support that. But you also answer Vladimir's question that engineers need to know MATLAB practically. So I'm curious whether or not you're seeing yet, or if you have a plan to assess whether or not the physics major and the physics discipline as something that people would be drawn to is affected by this teaching style. Are your, like practically, are your number of majors going up or down? Do you see any correlation? Do you expect to see any correlation?
It's very early for us to give any assessment of this. I'll tell you what I can tell you. None of this is backed by hard data, just because it's so young. But we ask students. I'm sure everyone here, we have student reviews of teaching at the end of the semester. And some students really resonate with computation. I love it. I love the computation part. I'm having hard with the pen and paper calculations. And some other students would say, I am not resonating with this. I much rather prefer the pen and paper calculations. And what I learned from this is not that anything is better or worse than the other, is there are some modalities resonate with some students and other modalities resonate with other students. So it's good to have both. I'm not answering your question directly, but the CLAS survey, all we are hoping is that students don't get confused more. Whether they are less confused, that's part of surveys that others have to do, or maybe we will do as part of the next grant.
Were there any surprises in terms of what I'll call sort of supporting infrastructure in the sense of assuming that all students have access to a computer, like whether you can assume that students will have access to a laptop like in the classroom, or will they have access to it in a discussion section, or like the way that like physically that the classroom was laid out to encourage collaborative work on computing assignments. I'm just curious if like from that overall infrastructure perspective, if there's anything that surprised you.
So it's a good question in the following sense. So I don't know how it's here, but we have classrooms in Minnesota that are designed for group work. Do you guys have classrooms with the round tables that you can do instructions in round tables?
Some.
Yeah, okay. So for example, in mechanics last year, by default, we were being assigned these kinds of classrooms, and I had to ask, I want to move to a classroom in which students can work together in round tables. So that's kind of the overhead that you have to make in advance. So students can actually work together, not in the regular class. Even in rooms like this, you can have students work together in pairs. In terms of accessibility to computers, no. We've been assuming that students can have their, and students can borrow laptops from our IT departments if they have problems. By and large, there were no strong surprises. But yes, some thought needs to be given in advance to this collaborative mode of instruction. You probably know active learning. Active learning can be done in small round groups. I've been doing this for many years, so I was not foreign to that. But if new instructors are coming on, we would need to make sure that they are part of this as well.
We have time for one more question. Anybody back here?
Can you answer why MATLAB and
Oh
not
yeah,
Python?
I'm sorry. I forgot. I'm sorry, I forgot. Yes. So we really had, when we started this 3 or 4 years ago, we thought about two options, Python or MATLAB. We did not include Mathematica because Mathematica was not going to serve well those students who graduate and leave academia. And we were not going to do C because the learning curve is steeper, and we were not going to do Fortran because Fortran is old. Well, some of my colleagues still swear by Fortran, and they say all of the large climate models are done with Fortran because it's faster. But anyway, we ended up with Python because we could not ask the students to take a Python class ahead of time. And we deemed that it would be simpler to have them just do an hour or two of the MATLAB on-ramp and benefit from the extensive help that is available from MATLAB. It was really balanced. I'm not going to advocate. You know, a couple of years later, 2 or 3 years later, just a couple of years ago, we came to the department and said, you know, we should really move to Python. And then the director for undergrad studies says, no. You start with MATLAB, stick with it, you know, don't make too many changes too early. We said, fine. It's not really important for us. I don't care. I'm happy with either this or that. This is part of these things that I'm not going to spend my political capital fighting with the director for undergrad education because I need his help elsewhere. You don't want this? Fine, I'm fine with that.
Okay, let's thank Shaul again for a great Q&A.